The James Webb Space Telescope, JWST, is mankind's most recent astronomical eye, connecting across unfathomable distances and catching light that has traveled for more than 13 billion years. This light, however, lets us know something other than a story of time. It uncovers the advancement of our universe, shaped and extended by its continuous expansion. As we peer back at the most distant galaxies, we are essentially seeing an ancient time, moving increasingly close to the beginning of the universe, the Big Bang. The theory of the universe's origin, a central story of modern cosmology, strongly proposes that our universe had a distinct start and is limited in age. Yet, from its commencement, this particular enormous beginning has been met with incredulity and challenges to its validity. These challenges endure even in standard cosmology. For a long time, the theory of the universe's origin held strong, particularly after the discovery of the cosmic microwave background, CMB, in the 1960s. This background radiation, a weak sweeping murmur across the universe, adjusted flawlessly with predictions of a hot, thick early universe. However, groundbreaking observations by the JWST have recently raised questions and brought up new issues about the Big Bang's authenticity. Through the amazing clarity of the JWST, NASA's vast time machine, we've seen groups of ancient galaxies far bigger and more diverse than anticipated, testing our understanding of the universe's earliest stages. As the telescope peers back to when the first galaxies formed, it offers humanity an exceptional view, one that the Hubble telescope was unable to fully access. Hubble was simply not sensitive enough to detect the very faint, redshifted light of these earliest galaxies. However, with JWST's cutting-edge capabilities, we're looking as far back as the very beginning of time itself. As we venture into this unknown region, we encounter a deep-rooted mystery. How did the first galaxies truly form? And does the universe as we know it really have a singular, conclusive beginning? It was once thought that the earliest universe was a hot, obscure spot, so dense that light itself couldn't freely travel. This implies that, regardless of how powerful our telescopes are, we can't observe anything further back with light. Yet we are not limited to light alone. New technological advancements are paving the way for the discovery of gravitational waves from colliding black holes, which could act as a new method to peer back into the universe's early stages, maybe even into the very singularity we call the Big Bang. The foundations of the theory of the universe's origin and its growing skepticism stretch back to the 1920s and 30s, when astronomers first observed that distant galaxies seemed to be moving away from us. This revelation, combined with Albert Einstein's theory of general relativity, set the stage for the Big Bang model. Einstein's conditions anticipated that a static universe would be unstable, requiring either contraction or expansion. Seeing this expansion suggested that the universe must have been closer together in the distant past, implying a violent beginning for the universe. The universe's expansion has several significant implications. Not only do objects move farther apart, but the light emitted from them also stretches, shifting to longer wavelengths over time. Since wavelength relates to energy, with shorter wavelengths being more energetic, this redshift method shows that the universe has been cooling as it ages. By rewinding this infinite expansion, we reach a point where everything would have been so hot and dense that neutral particles could not exist, leading to a uniform, searing hot glow. This glow was confirmed in 1964, when space experts Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, an omnipresent radiation field faintly repeating the universe's blazing beginning. Yet, as the JWST pushes the limits of immense observation, scientists are finding features in the early universe that strain the traditional Big Bang narrative. We see enormous, brilliant galaxies where there should be none, grouped in ways that defy expectations. So, if the theory of the universe's origin alone doesn't explain these anomalies, what else could? At the heart of the theory of how things came to be lies a singularity, a point of infinite density and temperature where the laws of physics break down. This is where space and time supposedly begin. But this concept, while compelling, has limitations. Imagine trying to describe the entirety of existence packed into an infinitely dense point. This is where our understanding reaches a stopping point. Although many aspects of the Big Bang model have been supported by observations and lab experiments, this initial singularity remains a puzzle, prompting the question, could the universe have had a different kind of beginning? In the quest to understand the universe, science has found ways to replicate similar conditions. For example, quark-gluon plasma has been created in labs, and matter-antimatter pairs have been produced to align with early universe predictions. Through these tests and by studying the cosmic microwave background fluctuations, we have a well-supported picture of the universe's development. However, critical mysteries remain. For instance, if all regions of space were once packed into a single point, why do we observe such uniformity in the universe's temperature? According to traditional models, regions of space should show varying temperatures since they wouldn't have had the opportunity to exchange energy or information. Furthermore, we might expect to find remnants from the hottest epochs, such as magnetic monopoles or spatial anomalies, but none are observed. These discrepancies open the door for new possibilities. Either the universe inherently had these uniform properties all along, or there was some mechanism that imposed these conditions. One candidate explanation is inflation, a rapid expansion theorized to have occurred before the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed this revolutionary idea. He theorized that before the hot Big Bang, the universe underwent a dramatic expansion. This inflationary stage could explain why the universe appears flat, homogeneous, and isotropic. After inflation, the universe would transition into the hot, dense state associated with the Big Bang, setting the stage for galaxies, stars, and planets to form. However, as researchers now acknowledge, even inflation doesn't explain every anomaly. For example, groundbreaking observations by the JWST have uncovered surprisingly large galaxies from the universe's infancy, suggesting an accelerated rate of development. Inflation alone doesn't account for these findings. JWST's incredible capabilities offer humanity an unparalleled look into the universe. This $1 billion infrared telescope has captured breathtaking images of the early universe, revealing a variety of massive, luminous galaxies from when the universe was just a fraction of its current age. While cosmologists previously believed they had a solid understanding of how matter coalesced to form the first stars and galaxies, the JWST's discoveries suggest much faster development than expected. These observations have stirred both excitement and skepticism among scientists, as some are forced to reconsider fundamental assumptions about the universe's evolution. According to astrophysicist Erica Nelson, enormous galaxies observed within the first 500 million. The advanced simulation hypothesis offers yet another alternative. This idea suggests that the universe we experience could be the product of a sophisticated simulation created by an advanced civilization. Proponents of this hypothesis argue that the precise laws of physics and the incredible fine-tuning of constants in the universe could be evidence of some form of external control or design. While highly speculative and controversial, it raises profound questions about the nature of reality, consciousness, and the origin of existence. Regardless of the theory, the tools at our disposal to explore the cosmos, particularly the JWST, are advancing our understanding of the universe at an unprecedented pace. The discovery of galaxies and structures that challenge traditional models pushes the boundaries of our knowledge, forcing us to reconsider how we view the universe's beginning, its evolution, and its ultimate fate. Whether the universe began with a bang, expanded through inflation, or arose through an entirely different process, the answers may lie in the far reaches of space, where new observations may continue to transform our understanding of the cosmos. One thing is certain. As we continue to peer deeper into the universe's past, we are opening new doors to uncovering the mysteries of our existence. Every discovery made by the JWST brings us one step closer to answering the fundamental questions about the universe, questions that have intrigued humanity for centuries. What we learn from these observations could reshape the future of cosmology, revealing the true origins of the cosmos and the forces that govern its vast, dynamic nature. As our journey of exploration continues, humanity stands on the cusp of potentially transformative discoveries, each one offering new insights into the most profound mysteries of existence. Whether we ultimately confirm the Big Bang Theory, uncover a more complex origin, or find something entirely unexpected, these explorations will continue to fuel the curiosity and imagination of future generations. With the JWST at the forefront of this cosmic quest, we are poised to answer some of the deepest and most important questions in science and philosophy. Questions about where we came from, how the universe works, and what lies ahead in the vast, mysterious cosmos. Extends making a void of dull energy. This model infers a constant pattern of creation, breakdown, and resurrection. Each of these speculations offers special experiences into vast starting points, suggesting new conversation starters about the idea of space-time and matter. While the theory of how things came to be stays the winning clarification, it has been tested and reshaped by new proof, furthermore, new viewpoints. The JWST, with its unrivaled responsiveness, is ready to open significantly more privileged insights of the universe. As the telescope proceeds its investigation, it might uncover replies that reshape how we might interpret the universe and maybe even highlight a profoundly new history. The James Webb Space Telescope, JWST, has upset our comprehension of the universe, giving information that is driving researchers to reevaluate essential speculations. Its disclosures are reshaping our comprehension of the universe's advancement and pushing the limits of what we thought was conceivable. While numerous of the peculiarities saw by JWST adjust with laid-out cosmological models, a few discoveries propose that we could require to change the course readings. The disclosure of inconceivably monstrous worlds shaped 200 or 300 million years after the Big Bang challenges the traditional course of events for galaxy development. In existing models, galaxies take more time to structure as they slowly accumulate gas and dust over billions of years. However, the perception of enormous mature galaxies in the early universe proposes that galaxy formation could have been far more rapid than previously suspected. Some researchers hypothesize that these early galaxies might have grown rapidly due to the impact of dark matter, or even dark energy, substances that are still inadequately understood, yet whose impacts appear to be turning out to be more critical in universe development. Likewise, JWST discoveries have incited new conversations about the nature of dark matter itself. While dark matter was conjectured to be responsible for the gravitational pull that holds galaxies together, JWST observations have suggested that galaxies could form and develop in ways that don't completely depend on dark matter, as previously suspected. This has prompted inquiries about whether the idea of dark matter is different from what was accepted or, on the other hand, if new yet-to-be-found forces are at work. Besides, a few specialists are looking into the likelihood that dark matter could be more confined than previously expected, grouping in regions of the universe with unfathomably unique structures than we envisioned. In much the same way, the idea of dark energy, the baffling force driving the accelerated expansion of the universe, has faced new examination. While dark energy was once thought to be consistently distributed, JWST's high-resolution observations are beginning to show subtle variations that could change how we see the universe's development. Could the impacts of dark energy be developing over time, or maybe acting differently on smaller cosmic scales? These inquiries are provoking cosmologists to refine their models and think about additional possibilities about the universe's destiny. In addition, JWST is opening new insights into the development of the first stars, or population 3 stars, which are believed to have formed from the primordial hydrogen and helium left over from the Big Bang. These stars are thought to be massive, hot, and brief, and they would have been responsible for the first generation of heavy elements through atomic fusion. However, JWST has uncovered proof suggesting that stars may have formed under conditions far more varied than previously suspected. The size and composition of early stars might have been affected by factors such as radiation from the first galaxies or the early development of space itself. This challenges traditional theories about stellar nucleosynthesis and suggests a more complex narrative for the early universe's development. Another fascinating part of JWST data includes the discovery of large-scale structures in the early universe, like the first very massive black holes. According to existing models, very massive black holes should have taken significantly longer to form. However, JWST observations of young galaxies indicate that these enormous objects were already in place within a few 100 million years of the Big Bang. How these black holes became so large so quickly is still an open question. Some researchers speculate that black holes may have formed from the collapse of enormous clouds of gas, while others propose that the merger of smaller black holes or the direct collapse of dark matter could have played a role. The presence of these early black holes raises the question of whether they were integral to the development of galaxies, as their massive gravitational pull might have played a crucial role in shaping their structure. As for cosmic evolution, the JWST's detailed observations of the early universe are beginning to provide clues that significant inflation, although a key part of current cosmological models, may require refinement. Inflationary models propose that the universe went through an extraordinary expansion following the Big Bang, explaining the uniformity of the universe. However, the discovery of structures like massive galaxies and very massive black holes in the very young universe could indicate that the inflationary process was much more complicated than previously thought. If inflation occurred in different ways across various regions, it could help explain some of the anomalies in the distribution of galaxies and matter. Furthermore, JWST's ability to capture data across different wavelengths of light is revealing a new level of detail in the distribution of cosmic elements. This data suggests that the composition of early galaxies may not have followed the predictable patterns expected by existing models. Instead, the presence of specific elements in unexpected amounts could suggest that chemical processes in the early universe were more diverse than once believed. This opens the door for new hypotheses on how the first elements were created and distributed. As these discoveries unfold, the implications for our understanding of the universe grow ever more significant. The theory of the primordial cosmic explosion will not have to be discarded completely, but it is clear that the story of the universe's origins is far more complicated than initially thought. Following JWST's discoveries, cosmologists may soon find themselves adjusting not just the details of the universe's past, but the very frameworks that govern how we understand space and time. Whether through the continued exploration of the early universe, advancements in theoretical physics, or entirely new observational techniques, the journey to uncover the true story of the universe is far from over. Each discovery brings us closer to understanding the vast and mysterious origins of everything we know.